my colleague Anuragan Chu on the NLTS conjecture, which you could think of as a first step towards proving the quantum PCP conjecture. So we've known for quite a while that calculating the lowest eigenvalue, or the ground energy of a local Hamiltonian, to a logarithmic number of bits of precision is a QMA complete problem.
Good morning, everyone. I'm wondering if Chinmay is going to be presenting in person from Simon's Institute.
Yeah. Hi, can you hear me? Mike?
He already started, actually, so he's here in the auditorium.
I wonder if there's no video.
Oh, no, I can't hear you.
No. Interesting. Now I'm on video.
Oh, no way.
Okay, let's try this again.
The video is on you.
Yeah. Now I see it. Okay. Hi, can you hear me?
So it seems like people are saying that
everyone else can. Okay. All right, I think I'll just continue then. So we've known that the local Hamiltonian problem to a logarithmic number of bits is QMA complete, and QMA, of course, being the non-deterministic version of quantum computation. And at the same time, we've also known from the celebrated PCP theorem that the estimation problem is actually just as hard in the case of classical Hamiltonians when you're just trying to get the first couple bits. And this, in classical local Hamiltonians, the analog would be NP completeness. So it begs the question that sort of just sits there as one of the big outstanding questions in quantum complexity theory is non-deterministic quantum computation as hard to solve approximately as it is to solve exactly? Or in a very specific form, what's the complexity of approximating the energy of a local Hamiltonian, the ground energy? Well, unfortunately, we don't know this problem, but we can try to make some progress towards figuring out the complexity of this question. So let's start off with something very basic, which is to say that if we believe that NP is separate from QMA, then if this quantum PCP conjecture was to be true, we would hope to say that approximating the energy is harder than NP. One way of saying that is that any classical proof that for energy approximation should require super polynomial length, right? It should not be in NP. The proof should be very long. But that's going to be really hard to do, because that would also imply just that NP was separate from QMA. So let's back up a little bit, even more, and try to say a simpler goal, which is that all classical proofs of a very specific form are going to require super polynomial length. And this will give us an advantage, at least as starting to get some handling as to what makes QMA hard. What gives it that edge over classical proofs. So we noticed one simple phenomenon, that if you have a local Hamiltonian H, you can calculate in polynomial time the energy of a state if that state is the output of a constant depth quantum circuit. And when we say polynomial time, I mean for a classical computer. So a classical computer in polynomial time can calculate the energy of a state that's the output of a constant depth quantum circuit. So that begs to say that if you had a constant depth state of low energy, then that in itself would be an NP proof of low energy, because someone could give you the description of the circuit that produces the state, that's a classical description, and then you could use this statement above to just check the energy and check that it was sufficiently low. So these constant depth states can potentially be certificates of low energy. They may not be certificates of the lowest energy, but they could certainly be certificates of low energy. So this leads to the very simple conjecture, the posited no low energy trivial states conjecture, or the NLTS conjecture, that there should exist Hamiltonians with no low energy constant depth states. As in, there is no classical certificate that comes in the form of a circuit description that would certify that the energy of this Hamiltonian was sufficiently low. Another way of saying this is you're trying to prove a lower bound on the complexity of all low energy states. So to go at this a little deeper, now let's try to introduce a little more technicality to these kind of open-ended loose statements, and let's formally state what we're talking about. So the quantum PCB conjecture says if you have a Hamiltonian system that acts on, say, n qubits, where the Hamiltonian terms are going to be necessarily local, so I mean that in two different ways. I mean that each qubit is acted on by only a constant number of Hamiltonian terms, and each Hamiltonian term can be described by its action on only a constant number of qubits. Then the question of calculating this energy has the following complexity. So if you're asked, given the description of the Hamiltonian classically as an object, how hard is it to approximate the energy up to some accuracy? And we know that the approximate the energy to inverse polynomial 1 over n squared, that's QMA hard, certainly. And the quantum PCB conjecture is asserting that that's also QMA hard when you increase this approximation factor a lot to a linear fraction. The NLTS conjecture, then, you could write in the following very specific format, that let's say we define the circuit complexity of a state as the minimum depth circuit required to generate that state. So by here I mean that there is a circuit, the gates are any 2 qubit unitaries, they don't need to be geometrically local, and if you trace out some of the wires, at the end of the day, the state that remains is your state. Then the NLTS conjecture formally says that we need to have a family of local Hamiltonians such that every state of low energy, every state of energy below epsilon n, these states cannot be described by circuits of constant depth, or another way of saying that the circuit complexity of these states has to be super constant. Pictorially, you could sort of imagine that the circuit complexity of states sort of drops as we relax the energy requirement, and it says that as long as the energy is below some threshold, some epsilon threshold, the circuit complexity is certainly super constant. So let's just elucidate the implication that we had stated casually in a more direct manner. So let's put these two powerful conjectures together. So imagine you had a quantum PCP statement that said something like, given a local Hamiltonian H, and you're asked if the minimum energy is either 0 or bigger than 10% n, and to say that was QMA hard. And you assumed that NLTS was false. So it said for every epsilon and every local Hamiltonian, there was a state of constant circuit complexity that certified that the energy was at least less than epsilon n. And so it just says that if NLTS is false, it says that every local Hamiltonian is going to have a state of low depth with low energy. So if we put these two together, we're going to find a contradiction. We're mainly going to find that NP has to equal QMA. So the way that kind of goes is, imagine you had a QMA proof that the minimum energy is 0. And that QMA proof basically looks like a state rho such that trace H rho is actually 0. But instead, since we're assuming that NLTS is false, we know there is a state of constant circuit complexity, sigma, such that the energy of sigma is going to be less than 1 over 20n, so say 5%. And what we can say is let U be the defining circuit for the state sigma, because it has low circuit complexity. And the claim is that the description of U is all you need as a certificate that the Hamiltonian had was low energy. And that description of the circuit U is a classical witness. So what do you have to just check? You have to check that if the minimum energy was actually 0 of the Hamiltonian problem, then you can just classically check that trace of H sigma is less than 1 over 20n. But if the minimum energy of the Hamiltonian was larger than 1 over 10n, then no matter what classical description you give, you're just going to get some state. And necessarily, that means that the energy of that state is bigger than 1/20n. So what you get is that if you're trying to approximate the energy of a Hamiltonian to just constant factors, and NLTS was false, then you would get that QMA equals NP. And this is crucially because the depth of the of U, the circuit constructing the witness, is constant. So if we're going out there and we're trying to prove quantum PCP, a first step, a very reasonable first step, is to try to prove this NLTS, to show that at least this very simple form of classical proofs cannot be used, to verify the energy of Hamiltonians approximately. And in doing so, what we're going to need to do is we're going to need to sort of provide circuit lower bounds for all the low energy states of some Hamiltonians. So let's dive into that exact question, which is we need techniques for proving the circuit depth lower bounds for Hamiltonians. And ideally, we want to do this without any computational assumptions. The first idea we have for proving circuit lower bounds is to use information propagation. So if you have a low depth circuit, interestingly enough, you have this beautiful result that the information propagates not too far because the circuit is low depth. So let's describe this in a following manner. Let's say we have a circuit U and we identify an input wire I, or input qubit I, and we define the light cone, Li, as all the output qubits that could be informationally related to the input qubit I through this circuit. And the idea is that because the circuit is low depth, the size of this light cone is bounded. It's at most 2 to the depth of the circuit. So in the case of small constant depth circuits, the light cone is only a constant factor bigger than the input qubit itself. And we have this very interesting property when we talk about low depth circuits, that if I want to know the value of the ith qubit, so if I trace out all but the ith qubit of the state rho after it's rotated by the unitary U, this is equivalent to first just looking at the reduced state of rho on that light cone and then rotating that. So there's a very nice simple proof of this. So you can show that for any operator A, I can rewrite this trace formalism of the measurement of operator A on the ith qubit as trace UA U dagger rho. And pictorially, this looks something like this. Here's the operator A. It's sandwiched between the circuit U and U dagger, and rho sits on the outside. But notice that a lot of the gates are right across with their complement gates, so you can just start to cancel them out because they're unitary gates and they cancel with their component, and you get this simplified picture. That all that's really left is the circuit U acting only on the light cone of that wire, and then you're left with rho. So what that means is that you can rewrite this as trace of UA U dagger rho on the light cone. And since this is true for any operator A, it tells you exactly the statement in green, that the value of the ith bit only depends on its light cone. The second powerful property we're going to need is this notion of global entanglement, which is a uniquely quantum property that you can have, which is that if you have two states, psi and psi prime, such that on small regions, they look the same. So on every small region, these two states look the same, then you can actually show that psi cannot be generated by a circuit of depth less than log d. So an example state, just to keep in mind for global entanglement, is the cat state. That would be the all zero state plus the all one state. This state is indistinguishable from the cat minus state, where instead it's all zeros minus all ones. Because on any size region other than all the qubits itself, this just looks like a maximally mixed state between all zeros and all ones. And so how do you sort of show this step? Well, you use the previous information bound, which is, let's assume that psi was generated by a low depth circuit U of depth some t less than log d, okay? Then what you get is that the size of any light cone is at most 2 to the t, and that's upper bounded by d. So then we start off by saying, okay, if I rotate psi by u, I'm just going to get back all zeros. So that gives me that first equality. And then I use this property that the information only depends on the light cone to switch psi for psi on that light cone. And now I just notice that, oh, the psi on the light cone, well, the light cone is really small, so it's exactly equal to psi prime on the light cone. And so I get the next equality. And then I put one more back together to bring me back to get that the ith qubit of rotated psi prime is exactly 0, 0. And then what that tells you is that psi prime is going to overall look like 0, 0 when rotated, which gives you that psi prime is equal to psi, and therefore you have a contradiction. Okay, so it's a simple proof that if you have this global entanglement property, you inherently have at least some circuit lower bound. So a question then is, how can we create states that have global entanglement for all the low energy states? So a good idea might be to start with code states for quantum error correction. So they are truly a fruitful source of global entanglement because you can show that every code state of an NKD code has the same marginals. And so the reduced density matrix on small regions is exactly the same for all the code states. And there's two different proofs I know of this. The first one you can show it follows directly from the Canil-Laflamme conditions, but I don't think that one's really intuitive. But the intuitive proof that I think about is that if the region is correctable, then I can recover the state back from the rest of the space. So that means that psi is recoverable from psi on minus r, on everything but the region r. And therefore, if psi r, the reduced density matrix of psi on that small region, did depend on psi, then this violates no cloning, because now you have the completely recovered state psi plus something which is partially correlated with it in general. So no information in this context exactly means that the reduced density matrix on that small region must be a complete invariant. It cannot depend on what state it originally started with, and that's why you get this property. So immediately from this property that codes have the same marginals, you necessarily see that codes are a form of global entanglement, as long as the distance is good. And if you have that codes have global entanglement using the previous steps we immediately get that every code state of a code that requires some circuit depth. And that circuit depth scales like log d, excuse me. In general, D's, it's like a good code. D will be like maybe square root n or polynomial in n, so that gives you log n up to constant factors. Now, the difficulty inherently is how do we take this property of global entanglement that exists at least for the code states, the zero energy states of this error correcting code, and extend it to the states of low energy with respect to the code. So an ideal idea, right, would be that if we could take any low energy state with respect to this code, and we could create that sort of imposter state, the state that, mimics it on all the local marginals, but is different from that state, then certainly, we would have a proof for the circuit complexity. That turns out to be sort of hard, but what we can show through this result of myself and Anurag Anshu from last year is that if you have a code and you can prove a circuit lower bound on all the states of low energy, and the circuit lower bound that we get scales like order minimum of log n and log 1 over epsilon. So when epsilon is a constant factor, this gives a constant depth lower bound on the circuit complexity. What we'd really like to say for the NLTS result is a circuit lower bound that's independent of epsilon. And we unfortunately are not able to achieve this, but we are able to give the first circuit depth lower bound for all states of low energy. And in particular, if you think of epsilon as any function that scales inversely with n, then this does indeed give you a super constant lower bound as to the complexity.
Quick question here, if I may, Chinmay.
Yeah.
Just for clarification, what Hamiltonian do you assume here so that there's a relationship between a code state and energy?
Oh, yeah, it's the Hamiltonian that defines the code. So in this case, it's going to be, we're going to just talk about an LDPC stabilizer code, and it's precisely the Hamiltonian defined by taking each check and converting it into a projector.
Great, thank you.
Yeah. And the sort of the proof idea is that while we don't know a proof that every low energy state satisfies global entanglement, we can't necessarily find the imposter. We're going to show that we can find some approximate imposters, states that mimic all the small marginals approximately. And in fact, we can show that for error correcting codes, not only can we find a imposter that mimics the marginals, but you can actually find many such imposters. And you're going to use the property that we can find many such imposters, along with the fact that each of these imposters is an approximate imposter, to indeed show a lower bound as to the circuit complexity. So perhaps I should pause here for a second, see if there are any questions that sufficiently confused everyone or not.
There is a question in the Q&A.
Sure.
I'll read it up. Did your version of NLTS assume that the circuits are spatially local? If not, in a non-local circuit, the light cone argument doesn't give you much, does it?
No, so the assumption actually is that the circuits are non-local. That's why we assume that the size of light cone scales like 2 to the t. If the circuit was assumed to be geometrically local, instead of the size of light cone being 2 to the t, let's say it's 2d, it would scale more like 2 times t, right? So you could actually get so the same results can be used to prove geometric circuit lower bounds, and you'll actually get much, much tighter geometric circuit lower bounds as a consequence.
I mean, it seems like here the number of constraints is the same order as the number of sites.
Yeah.
And if you ever consider it without that,
I think you have to be a little careful, because if you start to assume that the Hamiltonians, let's say, are not constant locality, then you can get very simple circuit lower bounds just based on the fact that if a Hamiltonian is k local, there's at least a circuit lower bound of k automatically. This is just because that you could imagine the Hamiltonian is just the projector onto a really random state. Circuit lower bound. So you have to be a little careful as to how you define it for Hamiltonians with non-constant locality. So the statement we had on the previous slide of a circuit lower bound is not, it applies to codes that we actually know exist today, and we can actually get very nice lower bounds. So one example is the Tillich-Seymour hypergraph product code, for which we know of a linear rate and a distance which is actually square root n. And another code that it does apply to very interestingly is the puncture toric code, where we assume the puncture toric code has a lot of holes, n to the 1 minus delta holes. Here the rate is not linear, but it's almost linear. And the distance is like scales like n to the delta. And here you get that a circuit lower bound on all states of energy n to the 1 minus 2 delta of delta log n. So if you think of delta as a constant, this says for like all states of energy n to the 0.99 or so, the circuit complexity of this scales at least like log n. What's probably incredibly interesting is that this toric code, the puncture toric code, it's a two-dimensional code, right? It just sits on the torus. And yet it displays this sort of form of robust entanglement that we didn't really previously expect would exist in low dimensions. Okay, to sort of start proving the statement for low energy states, maybe it's helpful to first think about sort of what do low energy states look like for a Hamiltonian. So if we imagine this big ball here is all the states of truly low energy, let's see what it contains. Well, in the beginning, it certainly is going to contain all the code space. Those have energy 0, right? Another option is that it contains states which are just L1 perturbations. I start with the code state, and I just shift it somewhere in the space by epsilon. And what I get is that this perturbation, doesn't change the energy too much because it's just a very small perturbation. And you could even generalize that to say that it just states so that every Hamiltonian term associated, the energy of each of those doesn't scale too badly. And you could contrast this with some notion of low error states, which is you take the code state and you change it up to on epsilon n qubits. You just completely change it, do whatever you want to a constant fraction of the qubits, but you don't touch the rest, right? And this low error state was actually an interesting regime that was initially studied as part of this problem by myself, Henry Yuan, Umesh Vazirani, and also Aram Harrow and Lior Eldar. And you could also generalize this to a notion of something I call combinatorial states. But the idea is that it's a very vast and diverse zoo of states. In particular, the states that you get by rotating by a small perturbation, those could really be affecting all the qubits. You could be physically changing all the qubits, while the lower error states only act on a very discrete set of qubits. It's sort of like at the very forefront, there's at least 2 different types of errors we need to sort of handle. And so that perspective is sort of nice in using. And it's particularly interesting, actually, that these bounds exist for error correcting codes, because you would think that an error correcting code would be would be really good at protect against like these low errors states, right? Protecting against discrete errors in a certain number of qubits. What's sort of interesting is that we can actually provide a lower bound for all these types of states, including these small ball perturbations. So let's start with that. Let's start with trying to see how to prove a circuit lower bound for these small perturbations. And we'll see that actually proving the problem in this restricted case provides us basically all the insight we need to generalize this to all low energy states. So the way to start this is, let's just say that we have some state psi, which is some distance delta from the code, and we just ask, what is the circuit lower bound of psi? And by the result I said previously, we know that for any code state, that's at least log d. And for simplicity right now, let's just assume that psi is a pure state and that the circuit generating psi is going to be a circuit without ancillas. These assumptions are not necessary, but it'll simplify the proof for the purpose of this talk. And here's the theorem we're going to show, is we're going to show that as long as the distance scales as square root of d, delta, is less than the rate, k over n, then for any state that is that distance, we actually can recover the same lower bound up to constant factors of log d. Okay, so here's what we're going to do. We're going to do the complete proof of this statement. I'm not going to skip anything. Every step of this should be answered. So here's how we start. We're going to say psi is that state again, and I'm going to introduce a new state. I'm going to call them theta, and theta is going to be the encoded maximally mixed state. So one way to think about that is that the code space is it's a k-qubit subspace of the whole Hilbert space, and this is just the maximally mixed state over that k-qubit Hilbert space. And now let's take a small region R, which we believe to be correctable. So it's a region of size less than d. And we're going to notice the following property, that the marginals of psi are a pretty good approximation on the marginals of theta. There's 2 steps. One is just the distance, psi is close to rho, and then rho is a code word. So by the local indistinguishability property that we showed, rho and theta have the exact same marginals. Okay, and now let's assume something that's going to yield our contradiction. So let's assume that psi was built by a low depth circuit. So there's a circuit U, and the depth of that circuit was small. It was smaller than such that 2 to the t is less than d. So what we get immediately is the statement in magenta that if I rotate that state psi by the unitary U, I get back to the all zero state, which in particular means qubit by qubit, the rotated psi looks like 0. And now we're going to put that together just like we did a couple slides ago in a very similar equation. Let's break it down. So the first equality on the very left side, that's just copying from the previous time. Then the green equality we see there is I'm saying that I can restrict psi to the light cone, right? The same sort of trick I'd involved a couple steps ago. I'm just now going to say I'm going to restrict psi to the light cone. And now I get this approximation factor, right? I get an approximation factor that came from the fact that psi on small regions approximates theta on small regions. And then I put it back together to get that the rotated qubit of theta looks a lot like 0, right? Looking at the whole equation left to right, I just get that the rotated qubit of theta looks a lot like 0. In particular, it says something very interesting, that the entropy of that rotated qubit of theta, just qubit by qubit, the entropy of that qubit is at most square root delta. This is just from the fact that it's really close to a pure state, right? So what does that tell me, though, is now I can add up the entropy. I first noticed that the maximally mixed state, because it's the maximally mixed state over this k qubit subspace, it has entropy at least k, right? But a trivial bound for the entropy of a state is the entropy of each of the qubits one after another. I can just add up the entropy qubit by qubit. And now I get this following fact that I get that k must be less than square root of delta times n. But that was precisely the assumption we, made in the opposite direction, so therefore we get our contradiction. And the only assumption we'd made was that psi came from a low depth circuit, and that will complete our proof. So let's pause for a second and see really how similar this was to the proof that code states have high circuit complexity. All we did differently is we noticed that we couldn't necessarily find an imposter for psi, but we could definitely find an approximate imposter, right? Using this equation 1, that psi looks fairly close to the maximum mixed state on theta. But what this actually tells me, though, is that not only did I find one imposter, but I found a lot of imposters, because theta was this maximally mixed state over the code. I found that psi was really had a lot of imposters, and I used that the fact that there were many approximate imposters to put it together to get an entropy contradiction. And this provides a technique for lower bounding all the low distance states. So now that we have a bound for low distance states, we're going to take this bound and we're going to lift it to bounding all the low energy states. And the way we're going to do this is we're just going to notice a very nice property that in the case of LDPC stabilizer codes, where all the checks are tensor products of a few Paulis, you get that not only does the code space, which is defined as the set of vectors that satisfy all the checks, but also every eigenspace of this code has this local indistinguishability property. The marginals are the same. And this is a very easy fact to prove just coming from the Kneel-Laflamme conditions. And then we can use this sort of at a very high level to argue a circuit lower bound for all low energy states by first breaking them up according to the eigenspace, and then eigenspace by eigenspace arguing a circuit lower bound. This is the sort of a really meaty technical argument, so we're going to skip it for now. And that is sort of what gives us this main technical theorem that I had alluded to earlier. Okay, so if given this almost NLTS conjecture that Anurag and I had proven, maybe the right thing to do is look back and say, what does this actually tell me about quantum PCP? Well, here's what we kind of hoped for from quantum PCP, was that if the NLTS theorem was false, then we knew that quantum PCP was false because we just showed it was a necessary condition. Unfortunately, or fortunately, however you want to look at it, we were able to show that NLTS is probably true, considering that we can prove these sort of lower bounds very closely. There's probably a few things left, some I's to dot and some T's to cross. And so the hope was that this construction of a family of NLTS Hamiltonians, it should have given us some insight into how to create quantum PCP Hamiltonians. Unfortunately, we saw that this property of NLTS is sort of general, right? It's actually somehow a general property of quantum error correction and didn't really require any strong assumptions as to the type of code or any serious strong properties of them. And so you might, condescendingly say, okay, at first glance, can you really learn anything? I mean, even more, the Hamiltonians that we were able to prove stuff about were stabilizer codes. And we know stabilizer codes are Clifford states, which means that they are sort of classically similar by other means. And I would say that's a very fair point. And in fact, what you might want to say is you need to now move towards lower bounding against all forms of Pauli-size classical proofs. And in particular, because you're able to show that Clifford states had circuit lower bounds, you might want to say, let's try some no low energy Clifford states conjecture, which is to construct a Hamiltonian family with no low energy Clifford states. That might be a very reasonable next question. And then all these techniques which I discussed kind of maybe fall out the window and we don't know what to do next. And you might even say, even further, more condescendingly, you actually should lower bound any state with inverse Pauli overlap with some low energy state. And in fact, we are able to do this in the case of the lower bounds from the result from Anurag and I, but we would have to say this at least in the Clifford setting as well. And maybe these techniques would involve insights behind stabilizer codes and error correction, because now you're trying to really combine two different challenging things. Starting to take something about Hamiltonians, which are non-Clifford, and prove some really interesting lower bounds. And this leads to maybe a more PCP-inspired technique for proving lower bounds. And this comes from this very simple idea that if we had a local Hamiltonian H, we could create a transformation to produce a new Hamiltonian G, which is just like negative a power of H. And what you can easily show is that this Hamiltonian G, at least the promise gap of the Hamiltonian G, increases by a factor P relative to the promise gap of H, just by doing this sort of amplification technique that is a core part of the classical PCP conjecture. And one thing we actually are able to show is that this amplification technique not only amplifies the lowest eigenvalue, as was shown in the PCP proofs, and then also a result for the quantum version, but it actually amplifies, it's solid against all low depth states. So you can show that if a state has low energy with respect to H, its energy and its low depth, its energy with G increases by a factor of P. But there's a fundamental issue in this technique that is rectified in the classical PCP theorem, is that once you start off with H and you do this amplification, the new Hamiltonian G is no longer local, and you're going to need some sort of locality reduction. And this is the part that's sort of missing, and maybe this is something we need to work on, but it should be known that in general this is false, and unfortunately it's false due to the exact properties of global entanglement that we had discussed earlier, that two states can look the same in all marginals, but they could be very different. So I know that doesn't really settle anything, but I don't think we should really be settling anything right now because the world is still quite open in this manner. There's some more smaller open questions here relating to technical details of the NLTS conjecture of myself and Anurag. But I think in the interest of time, I'll open up to any questions from the audience about any aspect.
Okay, questions. I don't know if I'm host or not, but Umesh sent me a message around 2 a.m. asking me to help. And so I'm willing to ask a question if nobody else has one. Oh, please go ahead, Sivarg.
Hi, Chinmay, can you hear me?
Yeah.
Okay, so thanks for the lovely talk. I want to just play devil's advocate for a moment and just ask a very naive question, right? Like, if your goal is to prove something like quantum PCP, right? It would seem to me that, trying to prove explicit circuit lower bounds on all low energy states, I mean, that seems like a very, very difficult way to go about proving quantum PCP, right? Because it almost seems like it would separate NP from QMA, right? You're proving that there literally is no good proof classically.
Not quite, right? Because
No?
not all classical proofs will look like low depth quantum circuits, right?
Sure.
Like, for example, you could always show that there was a low energy Clifford state, and that's going to be and you could just, provide me the stabilizer description of that state, and that's certainly sufficient. But that doesn't look like something that comes from a low depth circuit in the slightest.
Sure, but I mean, either way, I mean, you're assuming some form of ansatz, and you're trying to prove some sort of explicit lower bound, right? That's literally unconditionally separating like what's possible classically versus quantumly, and that seems like a very difficult thing to do in the context of separating complexity classes, right?
Mm-hmm. Yeah.
So that was it. That's just my comment. Just very naively, it's something that just occurs to me.
Yeah, I mean, and this was sort of the hope, right? The hope was that somehow trying to find this inherent property that a Hamiltonian with circuit lower bounds for all the low energy states would sort of guide you towards what a quantum PCP Hamiltonian would look like. But yeah, it seems like it's a more generic property than we thought. So it opens up a myriad of questions in that sense.
Okay, thank you.
I think we might have time for one more question. Aaron.
Well, I guess along the lines of that question, it raised the possibility that like maybe an approach to NLTS could just be looking for some polynomial time transform like Jordan-Wigner or some other kind of transform that, states that we very much think we can, like basically trying to prove NLTS while doing something that would never work for QPCP seems like it might be more promising. I don't know if you've thought about that beyond like stabilizers are one great example, but I wonder if you've thought about other families of states that are easy but not constant depth.
Yeah, I think that's a pretty good question. I don't really have any other ideas on techniques for proving lower bounds, so that I wouldn't know how to maybe start with those kind of states. But at the very least, constant depth states are also used as ansatzes in like QAOA. So this says, maybe they aren't as descriptive as we thought also. So it has a application in that sense also.
Oh yeah, good point, thanks.
Cool. I have a very quick question while maybe Leo gets set up and share screen, which is, so Chinmay, you had a little aside there where you said that you would be disregarding circuits with ancillas, but clearly ancillas grant circuits more power. So could you try having some ancillas assisted circuits along the lines Aram just described?
Oh, sorry, I should have clarified. The main theorem, at least, and the theorem in the paper will allow circuits with ancillas. It's just for the purposes of that nice, cute proof. It's easier to just make this statement without the ancillas for the moment. But yeah, you can generalize to circuits with ancillas and even mixed states. So
I see. It's because of your use of the information bound and the light cone, the Lieb-Robinson bound.
Yeah, you extend to ancillas by just considering the purifications, and the same thing you're going to need for anyways considering mixed states. So the technique, sufficiently solves both of those cases also.
Cool. Thank you very much. Let's all give Chinmay another hand. Okay, next up we have Leo Zhou from Harvard and Stanford, and he'll be telling us about strong universal Hamiltonian simulators. Leo, it's all yours.